Good morning. This is the fifth video about biochemistry in your AP biology curriculum. And in this video, we will be focusing on the properties of water. So the properties of water depend mainly on the polar nature of water. They depend on the polar nature of water. But before discussing the properties of water, we will go backward in order to highlight an important concept. We said that ionic substances like sodium ions, for example, or chloride ions cannot pass easily through the membrane. And you will find in many references that it's written that polar substances, and in particular ions, are repelled by the phospholipid bilayer. To me, this seems to be inaccurate because we cannot actually say that ions are repelled by the lipid tails, since the lipid tails do not carry any charge or almost carry no strong charge strong enough to repel or to attract an ion. But I think that what they mean by repelled is that, number one, that the lipid tails that are hydrophobic do not put any effort to attract the ions since they are not charged. So the lipid tails do not attract the ions. They cannot attract them actually because they are not charged. And the second reason why we say that ions are repelled by the lipid tails, that the lipid tails, being hydrophobic, have hydrophobic interactions between them. And these hydrophobic interactions help clumping the lipid tails together. And when the lipid tails are clumped together, they restrict the movement of ions and other charged particles. Now let's move on to the properties of water. The first property of water is hydrogen bonding. And as we said before, all the properties we will be explaining depend on one major property of water, which is polarity. As you know, the water molecule is highly polar, and it has oxygen in every water molecule. We have an oxygen atom that carries a partial negative charge and a hydrogen atom that carries a partial positive charge. Similarly, in this second molecule of water, the oxygen atom carries a partially negative charge and the hydrogen atom carries a partially positive charge. So it's normal that we can find an electrostatic attraction force between the partially positive hydrogen atoms and the partially negative oxygen atoms, not ions. They're atoms, but they're either partially positive or partially negative. That's why this bond between oxygen and hydrogen in the same water molecule is called an intramolecular polar covalent bond. But what about the electrostatic attraction force that exists between hydrogen and oxygen? We call it a hydrogen bond. So sometimes you are asked about the bonds in water, bonding in water. So when we talk about bonding, especially in water or any polar substances, we're going to talk about two types of bonding. And sometimes it is specified in the question. So you will be sometimes asked about the intramolecular bonds, Here by in, I mean concerning water. I don't mean inside water. So we have the intramolecular bonds and we have the intermolecular bonds. Of course, the intramolecular bonds mean the bonds inside the same molecule. Intra means inside, within the same molecule, within the molecule. But inter means between. So when we say intermolecular bonds, we mean between the molecules, not within the molecules, not inside the molecules. So now that we have understood the meaning of intra and inter, it's easy to deduce the bonds that are related to the molecule of water. So the intramolecular bonds will be polar covalent bonds, whereas the intermolecular bonds will be hydrogen bonds. So here, these are intermolecular bonds, and these are intramolecular bonds. Okay, these hydrogen bonds are weaker than the covalent bonds and weaker than the ionic bonds, but they are stronger than any other dipole-dipole interactions, because the hydrogen bonds are nothing but a specific type of dipole-dipole interactions, and we'll be very soon explaining what dipole-dipole interaction means on the next slide. But it's worth mentioning that these hydrogen bonds that result from polarity will themselves be one of the major properties of water, but also the root of all other properties of water. So all properties of water arise from polarity of the water molecule due to difference in electronegativity between oxygen and hydrogen, and the polarity of the water molecule results in hydrogen bonding between the water molecules, and hydrogen bonding will be the root or the cause of all other properties of the water molecule. Now we have just said that the hydrogen bonds between the water molecules lie in between the ionic and covalent bonds that are stronger and the dipole-dipole interactions. What are dipole-dipole interactions or dipole-dipole forces? They are attractive forces, or sometimes, by the way, they might be repulsive forces, like the ones we see on the diagram at the bottom to the right. So they might be attractive or repulsive forces, but I'm sorry. The dipole-dipole forces are attractive forces or repulsive forces. But when we talk about the bonds, the hydrogen bonds as one example of the dipole-dipole interactions, then we will be focusing, of course, on the attractive forces only and not on the repulsive forces. So in order to avoid confusion, let's first look at the dipole-dipole forces. Here, when you have a molecule with a partially positive end and another partially negative end, and when it's put in the vicinity of another molecule that also has a partially positive end and a partially negative end, then what happens is that if it depends upon the arrangement of the molecules. If it happens that the partially positive end of the dipole, what is the dipole? The dipole is the molecule, the polar molecule that has one partially positive end and one partially negative end. If it happens that the two dipoles lie next to each other in such a way that the partially positive end lies next or facing the partially negative end, then the dipole-dipole forces will be attraction forces. But if it happens due to the random motion of the dipole molecules that the partially positive faces the other partially positive end, or the partially negative end faces the other partially negative end of the other dipole, then the dipole forces will be repulsion forces. But of course, when we talk about bonding between the molecules, when we talk about dipole-dipole bonding, then we will definitely be talking only about dipole attraction forces and not dipole repulsive forces. Now, the dipole-dipole forces are weak and they have strengths that range from 5 kilojoules to 20 kilojoules per mole. If we look here at hydrogen chloride, as we agreed upon before, the hydrogen chloride molecule is a polar, the bond inside is a polar covalent bond, and the molecule is a polar molecule. So we will have a partially positive charge on the hydrogen end and a partially negative charge on the chlorine end. So if the HCl molecules are arranged like this, if we leave them without interfering, then it's very probable that they will be arranged this way. Why? Because the partially negative chloride end or chlorine end will be attracted to the partially positive hydrogen end. Now, the second characteristic property of water that helps, sometimes we don't ask you, sometimes we give you a very straightforward question, list or explain or describe the characteristics of water or the characteristic properties of water. But we sometimes ask you another question. How are the characteristic properties of water related to its polarity? But there is also a third question that is related to this, which is explain how the polar nature of water is important for the life of living organisms. We will see on the following slides, and through discussing the following characteristics of water, how these hydrogen bonds are important for optimum living of living creatures, for the optimum living of living creatures. So because of these polar structures and because of the polar covalent bonds, water will exhibit a high specific heat. What is the specific heat first? The specific heat is the amount of heat that is required by 1 gram of water. So we are talking about a mass, 1 gram of water. How much heat is needed? How much heat in calories or in kilojoules or in joules is needed to raise the temperature? And you know that there is a difference between heat and temperature. To raise the temperature of that mass of water by 1 degree Celsius. For example, if the original temperature was 37, then how much heat will be needed to raise the temperature of that gram of water so that its temperature would be raised to 38. This is what we call the specific. And when we say that water has a very high specific heat, this means that compared to other substances, 1 gram of water will need to absorb more heat than 1 gram of a metal, for example, for its temperature to be raised by 1 degree Celsius. How many times more? If you compare water to metals, it's 4 times, meaning that if you have 1 gram of water that needs an amount X, for example, of calories in order to, or an amount of, let it be 4 X's, an amount equal to 4 X's of calories for its temperature to be raised by 1 degree Celsius. So on the other hand, if we have 1 gram of copper, for example, then that gram of copper will require only 1x of heat for the same change in temperature to occur. And this means what? If you need a huge amount of energy for your temperature to move on to a higher level, then you resist changes in temperature. What we can deduce from the diagram that you see at the upper part of the slide is that water heats much more slowly than metals, or in other words, metal heat more rapidly than water. Why? Because metals are satisfied by a relatively much smaller amount of heat for their temperature to be raised. So their temperature is raised rapidly and easily. They do not resist changes in temperature, but water resists changes in temperature. So the water surfaces have a relatively stable temperature since they resist changes in temperature. This is very important because this means that marine biomes or biomes that consist of salt water and even fresh water, but mainly salt water, have a more or less stable temperature. This is very good for the living organisms that live inside, especially if these living organisms are invertebrates like fish, for example, or amphibians that cannot regulate their body temperature. So it's good for them that the water surfaces have a more or less stable temperature. On the other hand, this more or less stability of the temperature of the water biomes helps modulate or regulate or stabilize the temperature of the land nearby. Because now, if this is the land and this is the water surface, so if the land temperature is very high, then we will find that the density of air will become very low, and this hot air will rise upward to be replaced by the more dense or the denser, colder air. And this is what we call the sea breeze that happens in the morning. Sea breeze is the resultant of the fact that in the morning, the sand on the beach has a lower specific heat, and therefore it heats more rapidly. So its temperature is higher than the temperature of water. So the air next to it, or the air layers, will be hotter, will have a lower density, and we will see why. And those air surfaces or air layers will move upward because of their lower density, and colder air with lower density will come from the water. And the reverse occurs at night, because water will stabilize its temperature even when the temperature drops at night, but the land or the sand temperature will be much cooler, and the reverse will occur. So in the morning, you have a sea breeze, but in the evening, you will have a land breeze. So if you are sitting here on if you are sitting here on the seaside, then in the morning, you will find that the air currents will be coming to you from the sea. But in the evening, you will find that the air will be coming to you, or the air currents will be coming to you from behind. Okay? The third property of water is the high heat of vaporization. You all know that if the same substance, like water, for example, is in the liquid state, then it will have bonds between the molecules that are much stronger than the bonds in case water evaporates. So in the liquid state, water is more stable. The water molecules have less energy, less kinetic energy. They move less, and the bonds are stronger. If you give heat to the water molecules in the liquid state, this absorbed heat might be enough to break the bonds. And not only to break the bonds, which is the first necessary step. But the more heat you give, the more kinetic energy you give to the molecule. So you first break the bonds, and then you give the surplus of heat energy is added to the water molecules, increasing their kinetic energy. So the water molecules start to move back and forth and in every direction, and they are converted into gases or into a gas or the water vapor. And this is what we call vaporization of water. So vaporization of water is the conversion of water from the liquid state to the gaseous state. And in order for this to occur, we need to give energy to break the bond and then to increase the kinetic energy of the water molecules enough to allow the water molecules to break apart and move randomly in all directions. But the heat of vaporization has a specific definition. The heat of vaporization is the amount of heat energy that is needed to transform 1 gram of liquid water into water vapor. Of course, in case of water, the heat of vaporization is higher than in case of other substances that do not have such hydrogen bonds between them, because the heat of vaporization now will be first dedicated to breaking the bonds and then to increase the kinetic energy. So what makes the heat of vaporization of water high? The underlying explanation or cause of a high heat of vaporization of water is the hydrogen bonding. How can we apply, how can this be useful in our human body when the sweat glands in hot weather, as we have studied in human biology, when the sweat glands secrete sweat on the surface of, or excrete actually sweat on the surface of water, sweat consists mainly on the surface of the skin, sweat consists mainly of water with some dissolved salts. And if the temperature is very high around your human body, then this high temperature will result in elevation of the temperature of your body. And this is harmful to the normal functioning of your body cells. That's why we find that this sweat will evaporate from the surface of the skin. And in order for that sweat to evaporate, it needs to absorb some heat. What kind of heat? The heat energy that is the heat of vaporization. So it will absorb heat from where? It will absorb heat from the surface of the skin and the underlying tissues. And if that heat is enough to cause evaporation of water, then the water molecules will have the hydrogen bonds broken and will have more kinetic energy and will leave the surface of the skin. So evaporation of sweat is important because it means that this sweat has absorbed heat from your body to evaporate. And of course, if there was heat absorbed from your body, then your body becomes cooler and you have this cooling sensation that you feel upon evaporation of sweat. But there is one important condition. What is it? The important condition is that this absorbed heat should be equal or greater than the value of the heat of vaporization of water. There is another important point to highlight here is that in order for the water molecules to pass from your body to the atmosphere, water will pass as water vapor actually. So there should be a diffusion gradient, meaning that the concentration of water vapor around your body should be much higher than the concentration of water vapor in the air. And that's why we see that when we sweat in dry weather, the sweat evaporates on the spot to the extent that we might not feel sweating. Sometimes when you go to very hot countries that are also dry, that have a dry atmosphere, like in the desert, for example, away from water surfaces, you almost feel no sweating on the surface of your body. You just feel very hot because sweat evaporates. Any minimal amount that is formed on your skin will be evaporated, and it will be insensible sweating. But in a humid country, like in countries that are on the seaside, you will find that the sweat sticks on the surface of your body, and this means that you will not have this cooling sensation because sweat sticks on the surface of the body, stays there, and does not absorb any heat. Of course, because water has a high heat of vaporization, then it will absorb a huge amount of energy from your body, and it will have a significant cooling effect. The fourth property of water that's also related to polarity of water and to hydrogen bonding is the fact that water helps dissolution of the majority of substances in our daily life. And that's why we call it a universal solvent. And as we said before, when a solid substance, which is called the solute, dissolves in the liquid substance that is called the solvent, if it's perfect dissolution, if it's a real solution, then the solute no more appears in the liquid because it has intruded itself between the molecules of the liquid, as we said before in the previous videos when we talked about hydrophilic substances, especially ionic substances like sodium chloride and how they dissolve in water. And we said before that hydrophilic substances like sodium chloride dissolve in water. First of all, this is sodium chloride. Essentially, there is an ionic bond between sodium and chloride, but this ionic bond, of course, is a strong ionic bond. But in order for sodium chloride to dissolve, this bond has to be broken in order to separate the sodium particles or the sodium ions from the chloride particles or the chloride ions. And this is because the water molecules intervene in between. And we will find that the oxygen side of the water will be here attracted to the negative, the negative, partially negative oxygen will be attracted to the sodium ion, whereas the partially positive hydrogen will be attracted to the chloride ion. And this is the factor that helped the ionic bond, although strong, to be broken, and the water molecules intervene in between. And we have seen that it's not only about ionic particles or ionic substances like sodium chloride, but it's also about any partially charged molecules like polar molecules, hydrogen chloride, or the hydronium ion. And now we come to a very important and more difficult concept that says that because of these hydrogen bonds, again, if you remember, every property of water has been explained on the basis of the hydrogen bonds between oxygen and hydrogen. And these hydrogen bonds, again, depend on polarity. Another property that is based on the hydrogen bonding between the water molecules, I mean intermolecular forces, is related to the density of water. As we know, density equals density. Rho is the symbol of density. It is mass divided, the numerical value can be calculated from the formula mass over volume. So if the mass is in grams and the volume is in cubic centimeters, then the unit might be grams per cubic centimeter. And needless to say, that the density from this formula we can say that the density is directly proportionate to the mass, but on one condition, that the volume is fixed. So from the formula, we can say that the density is directly proportionate to the mass if you have a constant volume. So if the volume is constant. And on the other hand, we can also say that the density is inversely proportional to the volume if the mass of the sample you have is a constant. Let's look at the curve that shows you the relation between temperature and volume in water first, and then between temperature and density of water. But before looking at this diagram, let's first discuss what we have previously studied about the relation between temperature in degrees Celsius and the volume of the substance in cubic centimeters. Here, of course, we have the specific volume. The specific volume is the volume per gram, but let's consider volume only to make your life easier. As you know that as you go to the right, the temperature becomes more elevated. And we all know that the higher the temperature, if we have a higher temperature, then the substance will expand. And if the substance expands, this means that it has a greater volume. Then we have a direct relationship between temperature and volume for a specific mass. We always have to stabilize the other factor. We discussed the relation between temperature and volume. We don't have the right to say that the higher the temperature, the higher the volume, unless we have a fixed mass. So we discussed this for a fixed mass. Okay, so as the temperature gets higher, the volume gets higher, and therefore we should have a straight line like this, or at least a positive slope. But if we look to the curve representing the relationship between temperature and the volume for a specific mass of water, we will see what? We will see that from zero, or let's start here. We will see that if we go from right to left, because this will make your life easier. If we go from right to left, then we are going from a higher temperature, which is 10 degrees Celsius, to a lower temperature, which is 4 degrees Celsius. So what's happening to the temperature as we go from right to left? The temperature is diminishing. So what are we expecting the volume? What are we expecting the change in volume to be? We are expecting the volume to be decreasing. And this what exactly happened? As the temperature diminished from 10 to 4, the volume of water diminished from 1.003 to 1.001. But this applied only until the 4 degrees Celsius. But as the temperature diminished further, we found out that instead of diminishing, the volume increased once again. So the volume at 0 is higher than the volume at 4 for water, whereas in other substances, as you can see, the volume in 0 at 0 temperature should be much lower than the volume at 10 degrees Celsius, for example. This means what? From this curve, we can deduce that the lowest volume of water is at 4. Now, let's look at the the equation of density. Density, or the formula that represents density. Density equals mass over volume. And we have said that we are studying this for a fixed mass or for a constant mass. So in this relationship, if you have a fixed numerator or a constant numerator, then there is an inverse relationship. So if the lowest volume is at 4 degrees Celsius, then the highest density of water will be at 4 degrees Celsius. And this makes sense. That's why if we move on to the curve to the right, we will find that this curve represents the relationship between temperature and density. And this is, don't forget that whenever you draw a curve, you should give a title to that curve, and you're scored for this. If you forget, on a formal test, if you forget to write the title, then you lose a mark. So if the curve is scored out of 4, then you will get 3 out of 4, even if the rest is okay. So what title would we give to this curve? This curve shows the relationship between the temperature and density. And as we can see, since the lowest volume is at 4, then the highest density will be at 4. And then above temperature 4, the volume increases, so the density decreases. And again, above temperature 4, the volume increases and the density decreases. And below temperature 4, again, the volume increases and the density decreases. How is this important? This is important because let's first erase all the editing on the slide because it has been too messy, or it's becoming too messy. So here we can find that if the temperature of a layer of water is 0 and the temperature of another layer of water is 4, then the density of water, I'm just talking about water, not other liquids. The density of water at 0 Celsius is lower than the rest of the layers, is lower than at 4, for example, is lower than at 4. So let's look at this. Let's look at this diagram. For example, here in winter, you might have the temperature of the surrounding environment 0 degrees Celsius. So the uppermost layer of water will be at 0, whereas the remaining layers will gradually have warmer temperatures. Why do they have warmer temperatures? Because they are farther away from the surrounding air. And because water has the higher density at 4 than at 0, actually 4 is the maximum density of water, then we will find that this ice layer will be floating on the surface, whereas underneath we will have liquid water because the underneath layers are warmer. Not only are they warmer, but they are denser. The warmer they are, the denser they are, and that's why the bottom layers that are the densest will be the warmest. And this is important because it indicates that however low the temperature of the weather is, however snowy it is, yet fish and other marine organisms or aquatic organisms will be rescued by those deeper, warmer layers underneath. So you look at the water surface, you find it frozen, and you might have the impression that it's all frozen. No, underneath we have warm water. So this is important because, as we said, the importance of the fact that water density is maximum at 0 is that in winter, as you can see here, in deep oceans and deep water surfaces, ice will float on the surface and it will insulate the outside very cold air from the underneath warm liquid water to help survival of the living organisms. But what happens, on the other hand, when the weather improves? When the weather improves, we will find a very interesting phenomenon that is called spring overturn. Now, we have just explained what happened or what happens actually in winter. Imagine now that we moved on from winter to summer or first to spring, and the temperature of the surrounding weather rises from 0 degrees Celsius to 8 degrees Celsius. So what would happen? The surrounding, this ice at the top will melt, because this ice will if the surrounding air is at 8, then heat will be transferred by conduction to this ice, and the ice will be converted into water at 8 degrees Celsius. But the underlying layers, they will get definitely warmer because the heat will also be transferred to the deeper layers, but they will not be at the same temperatures as before. So the 0 degrees Celsius has been converted into 8, and the underlying layer becomes now 7 and not 1, and then 6, and then 5, and then 4. So what happens is exactly the opposite. Here, the coolest layer is at the top and the warmest layer is at the bottom, whereas here the warmest layer stays at the top and the coolest layer is at the bottom. Why does it stay at the bottom? It's not because it is the coolest layer. It is the coolest layer because it is the farthest away from the atmosphere around. That's why it's the coolest layer. But why does it stay at the bottom? Why doesn't it float at the bottom? This is because the bottom layer is at 4, and only when the bottom layer is at 4, that it is the densest, and it sinks at the bottom. Is this important? Yes, because what happens actually is that the ice that was at the top melts first to melts and becomes 1, and then 2, and then 3, and then 4. And when it becomes 4, it sinks at the bottom. When it sinks to the bottom, it carries with it all the oxygen from the atmosphere that has dissolved in the superficial layers before getting frozen. Meanwhile, the bottom layers, which were warmer, because they are warmer, like the 8, for example, will always be at the superficial layer. And when this occurs, this looks like an overturn, as we call it spring overturn, because it starts at during spring. And during this overturn, the coldest layers at the top become warmer until they reach 4 and sink to the bottom, carrying with them all the dissolved oxygen. And the warmer layers will thus be pushed to the uppermost layer, or in other words, more truly speaking, the bottom layers the uppermost layers that are in contact with the temperature outside and that are at 8 will be at the top, and the bottom layers that have raised to the superficial layers carry with them all the nutrients that come from the bottom of the ocean. Where do these nutrients come from? They come from the decomposition and the degradation of all the dead bodies at the bottom of the ocean. And now we move on to another property, that is cohesion property. Actually, we do not talk about um, um, adhesion between water molecules, but we talk about cohesion between water molecules, because cohesion properties are, or cohesion forces are attraction forces between similar molecules, whereas adhesion forces are attraction forces between different molecules. Now, if we look at two water molecules inside a xylem vessel, you know that the xylem vessels, or even a glass tube, xylem vessels are made of, their walls are made of cellulose fiber. Xylem vessels are the vessels that carry water upwards inside the plant, and those xylem vessels are formed of cellulose fibers and they are negatively charged. Similarly, if you have a glass tube, glass is negatively charged. So what happens here is that this is a cartoon animation of two water molecules. So you can say that the water molecules are attracted together by what we call cohesion forces. But similarly, they are attracted to the walls of xylem by adhesion forces. Of course, the animation is not very accurate because an oxygen atom cannot have a bond with another oxygen atom, but it's only to tell you that there are cohesion molecules between similar molecules and adhesion molecules between water molecules and cellulose or glass molecules. If we look here, this is a glass tube, and that glass tube is a capillary tube, meaning that it is a tube with a very, very small diameter measured in fractions of a millimeter. Why is the study of capillary glass tubes important? Because all xylem vessels inside the plant are nothing but cells that have been converted into vessels or tube-like structures. So actually their diameters are measured in micrometers. What happens when you have water inside a capillary tube? You will have cohesion forces between, let's consider the top layers of water. You will have cohesion forces at the surface between the water molecules. And similarly, you will have adhesion forces all around at the circumference or at the periphery between the water molecules and the glass molecules. And because in case of water, the adhesion molecules with glass are greater than the cohesion forces between water molecules, you will find this concavity of the water molecule, because these adhesion forces that are pulling the upper surface of the water molecule all around from the periphery is much greater than the cohesion forces that tend to make the water molecules coalesce together in the smallest surface possible. They are forced to be raised from the periphery because of adhesion molecules, and therefore you will see this concavity of the upper surface. But if it's not a capillary tube, if it's a big container, you wouldn't see this concavity, although there are adhesion forces, but the surface is so large that those adhesion forces at the periphery cannot raise the whole surface, and you can see a more or less horizontal surface. In case of mercury, for example, if you put, and of course, as I've just told you, the smaller the diameter of the tube, the more you can see this concavity of the upper surface of the water, and that's why this concavity is best seen in capillary tubes. Adhesion forces help pull the whole water column upwards, whereas cohesion forces, because you have other layers of water molecules, cohesion forces are present in all directions, and they help continuity of the water column, and they help you raise, or they help the adhesion forces pull the whole water column upwards without breakdown, without interruptions. Because if the water column is not continuous and if it breaks down, you can see air bubbles in between, and those air bubbles result in discontinuity of the what, or you can even find vacuum or space between the water molecules, and this will intervene with or will hinder and prevent the upwards rise of the water molecules in xylem or in capillary tubes, and this might lead to death of the plants. In case of mercury, for example, but this is an extra piece of information, you will find that in a capillary tube, the uppermost layer of mercury is a convex surface. Why? Because in mercury, this is exactly the opposite. The cohesion forces between the mercury molecules and that make the mercury molecules tend to coalesce together is more than the adhesion force that helps the elevation of the mercury column in the capillary tube. And this entails a very important result, that water molecules rise more easily upwards and show capillarity better than mercury, because the water molecules do not have strong cohesion forces. On the other hand, they do have actually strong cohesion forces, but the adhesion is larger. How can this apply to real life? This applies to real life with a phenomenon called transpiration pull cohesion adhesion. So what is transpiration pull cohesion adhesion? If you look here at a leaf, for example, that is connected to a stem, and here we have the xylem vessel inside the stem, and here we have the root cell that absorbs water. So first of all, the root will absorb water by osmosis, and osmosis is a pushing force because it pushes water from an area where we have a higher water concentration to an area where we have a lower water concentration. So here, water enters by a pushing force. But on the surface of the leaf, transpiration occurs. And transpiration is evaporation of water from the surface of the leaf through the stomata, which are the spaces in between the epidermal cells of the leaf. When you lose water molecules by this specific kind of evaporation that is called transpiration, then there is kind of vacuum here. So water molecules will be moved upwards to fill in that vacuum. So transpiration pulls on the underneath water molecules. That's why we call it transpiration pull. So the main drive for elevation of the water molecules or the upwards rise of the water molecules in xylem vessels is the presence of this transpiration pull. But transpiration pull alone is not enough. Transpiration pull is helped by cohesion and adhesion. That's why if you were asked to explain the cause behind or underlying the rise of water or the elevation of water in xylem vessels in very tall plants like palm trees, for example, we're going to talk about these three factors: transpiration pull, cohesion, and adhesion, although transpiration pull is the most important one. Of course, we have just talked about capillarity, so I'll be skipping that slide. And now we talk about one important property of water, which is the surface tension of water. We have all seen that sometimes on certain water surfaces, you can see a very small insect walking on the surface of the water as if the uppermost layer of water was a stretched out membrane. And this is what we call surface tension. When you're tense, you're tight. And tension is the state of being stretched out or being tight. And surface tension is the property of the surface, very superficial thin layers of water that look tense because they show strong attractions towards each other, as we will see on the next or the previous slide. I no more remember, but the water membrane will look stretched out and a bit concave, as if it is as if it were a concave stretched out membrane. And all this is due to the hydrogen bonds between the water molecules. Now, if we look at this bottom water molecule, the water molecule in the depth of water, of course, this water molecule in depth is surrounded by water molecules from everywhere. And there are hydrogen bonds that connect this water molecule to the surrounding water molecules. So at the end of the day, you will find that this water molecule has attraction forces with all the surrounding molecules, but each two opposite and equal attraction forces will cancel each other. So at the end of the day, you will find that sigma F, or the resultant of the forces, is 0. So at the bottom of the ocean or in the depth of water, the deep water molecules stay in place. It's true that they have attraction forces with all the surrounding molecules, but these attraction forces, it happens that these attraction forces cancel each other, so the resultant is 0. If we look here at the tension forces on this molecule, you will have equal attraction forces. Imagine, for example, you have a molecule here. So this molecule is molecule A and B, for example. So molecule A is attracted to molecule B, but similarly, molecule B is attracted to molecule A, and they cancel each other. Similarly, if we have a third molecule C here, the same applies. So it is supposed that the molecules on the surface of water also stay in place, but there is a great difference. The difference here is that for the deeper molecule, the forces were surrounding them all around. But here, if we look at the molecule to the right, you can see that it's true that there are neighboring molecules like molecule B and C, but here there are unequal forces because at the top, there are no forces of attraction. These are air molecules. But at the bottom, there are cohesion forces that attract to the bottom. Let's look at the resultant of these forces. If we look at these forces that represent all the forces that surround this molecule in the center, we will find that force A cancels force B. We will also find that we have two other forces, C and D. The resultant of C and D is that force, or let's say it in a different way that might be easier to you. Let's consider first the simplest forces. We have a force of attraction A to the right. We have a force of attraction B to the right, and a force of attraction C to the bottom. The resultant of B and C is Y, and the resultant of A and C is X. So these are the two resultants. And at the end of the day, the resultant of X and Y is also a downward force. So sigma F, the resultant of all the forces, is a downward force. And that's why the central part of the water is attracted to the bottom and looks concave downwards. By having studied or explained the surface tension of water, water, we would have finished all the properties of water. Thank you, and we will be discussing the rest of our biochemistry unit on the following videos. Thank you.